This is AQA A-Level Chemistry. It's a Year 12 topic, haloalkanes, and this is video number 3. In part 2 of this series, we took a look at nucleophilic substitution mechanisms, the principles that underpin them, and we looked at using OH- ions as a nucleophile. In this one, we're going to take that a step further forward and look at the other 2 common nucleophiles that are discussed in the AQA course. As always, I'm going to recommend that you try the activities as you go through, pausing the video and then checking how you've done. So, we have looked, as I've said, at KOH yielding OH- ions as a nucleophile. We're now going to see what you think would happen if we instead used cyanide ions. And the cyanide ion is, hopefully you can work out from here, Cn-. We know it's Cn- because it's bonded to an Na+. So have a go at the mechanism and see how you do. First of all, be really mindful of the question. It asks for chloromethane, not chloroethane. And I'm going to draw out my nucleophile, my Cn-, which we can see here. I've highlighted the blue, but I'm recognizing that this is the reagent and this is the nucleophile. So then I need to start representing what's happening within the mechanism. I need to show where the attack takes place, and I do that using curly arrows. I've got my lone pair of electrons and my arrow going towards the delta positive carbon. And because that would mean 5 bonds around the carbon, that can't be sustained, so we need to lose something. And it is the halogen that goes, and we represent that with a curly arrow from the CCl bond going to the chlorine. Now that takes us to our product, and you can see here I've got my CH3, my Cn has replaced the Cl, and I've got my Cl- ion. So now let's have a think about the name of the compound that you've just made, CH3CN. Cn has a suffix nitrile, has to be on the end of the carbon chain, so we don't need to number it. There is a very good chance that you may have incorrectly decided that this is methane nitrile. But you've got to remember that this carbon in the Cn is an extension of the carbon chain. So it is actually ethane, and then the Cn gives us the nitrile, ethane nitrile. And there's another really important component to this name, and that's this E. This E has to be included in the name. It will be underlined in mark schemes. That's how important it is. Ethane nitrile will lose you the mark, however much understanding that you have of what's going on in the chemistry surrounding it. Okay, why would this be of huge importance to the chemical industry? What I hope you can see is we've done something that's very, very unusual. We have extended the carbon chain, but there's a key word here. We've controlled the extension of the carbon chain. It goes up by 1. Now, we've seen extension of the carbon chain in free radical substitution mechanisms, but they are not easily controlled. You don't get one defined product at the end. So this is massively important. Okay. We also need to know a couple of extra steps on this one. So you have got to remember what we're going to look at here. Try and make sense of the information that's been provided and complete this equation. Remember, this is not a mechanism, it's just an equation. So we are told that the ethane nitrile is reacting with water and it's reacting with HCl. And from there, we're making ethanoic acid and we're making ammonium chloride. So I've got all of my components in there. I now just need to balance the equations, balance the whole equation. And I've got 2 oxygens here, 1 oxygen here. So I put my 2 in, and that now takes me up to 4, 5, 6, 7, 8 hydrogens. And I've got 3, 4, 8 hydrogens there. Job done. We also need to know how nitriles can be converted into amines by hydrogenation. Again, have a go at this equation and see what you can do. So my ethane nitrile and my H2, obviously remembering hydrogen is diatomic, and I am making the amine, which you have seen in, or will see in further reactions, depending on which way around you're looking at this. There are ways of making amines alternatively. Now from there I need to balance it again, and it's 2H2. And this question about the catalyst relates to things that you may have discussed at GCSE. Hydrogenation. A really common hydrogenation reaction is hydrogenation of alkenes to make alkanes, and we use a nickel catalyst, and it's the same as we use here. So what's the reagent and what's the nucleophile in the mechanism that's provided here? Well, the nucleophile is the Cn-, that's the electron rich, it's got the double bond that it can donate, but the reagent is not Cn-. The reagent might be KCN, it might be NaCN. The reagent must be something that you can get in a bottle, and you can't get cyanide ions in isolation. So we're going to move on and we're going to look at ammonia as a nucleophile. So have a go at this mechanism, see what you can do. And in the first instance, I've got my two curly arrows, exactly the same as we've seen before. And we're going to summarise all of these at the end so you can see just how similar they are. That then takes me to this product. My NH3 has gone on the end. I've drawn it as display for a very important reason. There's also something missing here, and that's the fact that this N is now positive. That doesn't make it particularly stable. So we have a second step to this mechanism, where a second ammonia acts as a base. So we need to think about what that means. What is a base? And hopefully you remember that a base is a proton acceptor, protons being hydrogen ions. So the NH3, instead of attacking the positive, acts as a base and attacks the hydrogen on the N. Could have been any of those hydrogens. But that then means that the NH bond can no longer exist, so the electrons move in to the positive N, which actually takes the positive charge away. So the whole equation, the whole mechanism I should say, we see here. I get an arrow going in here, I get an arrow going to the chlorine, I get my structure, and I get my two arrows to represent the 4 marks that are really available. And once again, what's the reagent and what's the nucleophile? Well, the nucleophile here is NH3 because that's got the lone pair on. Unlike the other two examples, the reagent is also NH3. Ammonia does exist as a stable compound, so we don't need to consider anything it might be connected to, bonded with, etc. I'm going to finish off this video with a little summary of the 3 nucleophilic substitution mechanisms. And if I draw them all out side by side, you can see I've got my 3 different nucleophiles here. They all attack in exactly the same way, the curly arrow going to the delta positive carbon. They all lose their chlorine. That could be a bromine, could be an iodine. But I've got the same arrow in place there, so lots of similarities so far. And I get to the product where I've substituted my chlorine for the nucleophile that I've added, and I've created a chloride ion. Now here is where we've got to remember the differences, and I'm going to start with the ammonia that we've just seen, the second step to make the amine. When we look at the reaction with Cn-, we have to remember that that extends the carbon chain, and we have to remember that it can be converted into an acid or an amine. So there's a common first step, and there's an extra piece of information for each of them. And we've not looked at extra information with the OH- ion, but we are, in the next video, going to consider the alternative elimination mechanism that runs alongside it. That takes us to the end of this video. Thank you for listening, and goodbye.